Hey kids, bet you didn't think I'd have that with me. All right, enough of making fun of my coffee jokes. This is coffee. It's like the elixir of life. I know that says day 8, but it should say day 7. Sorry, children. Day 7. Got a few mistakes in this one. We'll fix them. Hopefully you found them. So, let's get started. This is our practice test. Again, let me just warn you. First of all, if you have not subscribed, including my own students, if you haven't subscribed, please hit the subscribe button. Man, you're not doing me a favor. www. All these videos can be found in nice, easy, organized fashion at nkinfinity.com. Now, I am going to be doing a bunch of new stuff for review. First of all, I'm going to take all of my old, what I like to call spirals, and make videos of all those pretty soon. And I'm also going to be doing, I think I'm going to try my hand at some live streaming, and we'll see how that goes. Some live streaming review for that Regents exam, and you're all welcome to join in. So let's get started. This is a practice test. Unit 9. Oh my gosh, 2 units left. We're almost done with this one. We're almost done with the school year. All right, kids, if I ask you to list the sample states, don't forget that I'm going to ask you to do it in curly braces, all right, in set notation. And I'm just going to ask you to list them. I can do heads 1, heads 2, heads 3, heads 4, heads 5. Oh, wait, hold on. There's only 4. I thought it was a spinner. All right, tails 1. I did think that on the paper answer key as well. Tails 2, tails 3, and tails 4. Of course, I was using red pen and I couldn't erase. That's it. There's the sample space. All right. Question 2. Mr. and Mrs. Smith have decided they're going to have 3 children. Draw a tree diagram to show all the different combinations. Okay, so here they are. Boy, we're about to have a kid. I wonder what it's going to be. Well, it could be a boy or it could be a girl. Like, wow, we're about to have another kid. I wonder if it's a boy or a girl. Wait a second, we had a girl first? Oh, then I could go boy second or, 2 girls? Ooh, okay, that's not so bad. All right, so I had a boy first, and then I had another boy, and then I had 3 boys. I'm in trouble. Boy, boy, girl. I could go boy, boy, girl. Or I could go boy, girl, and then boy or girl. So a simple tree diagram, not a big deal. There it is, all of its glory. So how many different ways are there? There's 8 ways. Now, you could use the counting principle, says 2 on the first way, 2 on the second way, and 2 on the third way for a grand total of 8 different ways. So let's answer these questions. What is the probability of having 2 girls? Well, let's see what this looks like. 2 girls. I can go girl, 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 or girl, girl, boy, right? So there's 3 separate ways of having 2 girls. Now, maybe it's even in your best interest to kind of come over here and go, okay, this is boy, boy, boy. This is boy, boy, girl. This is boy, girl, boy. This is boy, girl, girl. This is girl, boy, boy. This is girl, boy, girl. This is girl, girl, boy. And this is this is girl, girl, girl. I know it looks like 666. I didn't mean that. Really, I didn't. Let's go girl, girl, girl. Okay. So what's the probability of having 2 girls? There's 2 girls, there's 2 girls, and there's 2 girls. So that would be 3 out of 8. What is the probability of having at least 1 boy? Now remember, 1 boy could be 1 boy, 2 boys, or 3 boys. And there's all these ways except for girl, girl, girl. So that would be 7 different ways out of 8. What is the probability of having 2 boys followed by 1 girl? Now, this is different than just having 2 boys. This is 2 boys followed by a girl. And there's really only one way to do that because the 2 boys have to come first. So it's got to be boy, boy, and then finally girl. And finally, what's the probability of having no girls? I'm just kidding, girls. I'm just kidding. But you have to admit, you argue with your moms a lot, don't you? Yeah. All your girls are like, yeah, I argue with my mom all the time. Yeah. It makes being a parent a lot of fun when you argue with your mom. You're like, Mom, I don't want to do that ever. Do it. No. Do it. No. Stop arguing with your parents. Anyway, boys just kind of do it because we're tools. We just kind of do what we're supposed to do. You girls are just meant to argue and always be right, which in my family is almost always true. But never mind. Anyway, 1/7. There's one way of getting no girls. What is the probability of having no girls? That's one out of 8 ways. Excuse me. All right, moving on. In order to make his password very complicated, I wonder who he has. In order to make his complicated, he has. I should have put somebody in here. Decided to start with either a this, or this, followed by 2 vowels, 3 digits, and ending with the same vowel it started with. So this is going to be 5 blanks. First blank, 2 vowels, 3 digits, and some symbol again. Well, as I go through these, I have 3 symbols here to pick from. So there's 3 here. Now vowels, there's 5 vowels. So I can put a vowel here, I can 5 here. Now it didn't say I couldn't repeat it, so I could go AA or EE or OO or OOOO. And then 3 digits. Now you got to be careful with digits. Remember, those are 0 through 9. That's 10 digits. 10, 10, 10. Now this is a little bit tricky part. It says it ends with the same symbol it started with. Well, if it ends with whatever I put here, I don't have a choice. I can only put 1 there. So if I put this % symbol here, then I got to end. Then I don't have a choice. I have 3 choices here, but whatever I decide here, I got to end with it as well. And I'll grab my calculator and multiply that out. Let's see, that's 20. That's 70. Oh, well, this is 75, and this is 1,000, so that's 75,000. Don't need my calculator for that. All right, 75,000. The school lunch program has decided to get a little more creative with their choices. Today they had the following items. How many different meal choices are there? And I should have said consisting of 1 entree, 1 vegetable, 1 dessert, and 1 drink. I should have said that in the problems. I didn't. But there are 4 choices for, 1, 2, 3, 4. Oh, wait, fried chicken. 1, 2, 3, 4. Yeah, there's 4 choices for that. There are 3 choices for a vegetable. There are 2 juices, or 2 drinks, and 2 desserts. So if I multiply that out, that's 48 different meals I can make with it using the counting principle. Jenna will only eat pizza and corn. So Jenna will not eat this, and she'll only eat corn. Well, that means I'm going to be limited down to 1 choice for the entree, 1 choice for the vegetable. Great. Close. 2 choices for juice and 2 choices for this. So that really only limits me to 4 choices. What is the probability a meal chosen at random does not have peas? Okay, so now wait a second. We're talking probability, right? So we're going to need a fraction. Let's see. Does not contain peas. So basically, I just got to eliminate peas from my choice. Well, that means I got 4 entrees, 2 vegetables, 2 juices, and 2 drinks, and 2 of these. So if I multiply that out, I get 32. But I can't just say 32. That's how many different meals contain it. What's the probability? It would be 32 out of 48. All right. I hate when my voice gets out of sync with my mouth. It's really annoying, and I apologize for that, but it is technology. I got to do what I got to do. So if it gets out of sync, sorry about that. So here's a tree diagram. We've seen this one before. This is for flipping a coin and rolling a die. So what is the probability? So it's got to be a fraction of getting a prime number. Well, the first thing I got to realize is there are 12 possibilities. 2 on the first, 6 on the second, multiply them, I get 12. Now, prime. 1 is not a prime number. The definition of a prime number is it has exactly 2 distinct factors. 1 and itself. 1 only has 1 distinct factor. So 1 is not prime. So 2 is prime, 3 is prime, and 5 is prime. 2 is prime, 3 is prime, and 5 is prime. So that would make it 6 out of 12. Or if you want, it's just a half. What is the probability of getting a heads followed by an even number? Okay, so let's look at that. A heads followed by an even number. Heads, heads, and heads. Well, there's 3 of these out of a total of 12. So 3 out of 12. That's it. All right, given a standard deck of cards, what's the probability of pulling a single card and getting a spade or a face card? Since there are 13 spades and 12 face cards, then I know the probability. Now, wait a second. This is an or statement. So the probability of a spade or, let me do this in notation that's meaningful, or a face card is equal to this probability of spade plus the probability of face card minus the probability of a spade and face card. All right, so the probability of spade, 13 out of 52. The probability of a face card, 12 out of 52. Now, I have to subtract off for the spades that are also face cards. That's the jack of spades, the queen of spades, and the king of spades. So I got to get rid of those 3 because I've counted them here and I've counted them here. So I got to get rid of them, 3 out of 52. So let's see, that's 25, 22 out of 52. Just checking my answer key, kids. All right. What's the probability of getting a red card or a number less than 4? So this is probability of red plus the probability of a number less than 4 minus the probability of red and number less than 4. All right, so this is going to be probability of red. Now, I could put 1/2 there. You know, in effect, it is in fact 1/2. But because I'm going to have all these other fractions that are going to have 52 as their denominator, I'm just going to leave it as 26 out of 52. Plus the probability of a number less than 4. Okay, so that's an ace, a 2, and a 3. Now, it has to be less than, so you can't include 4. But there's 3 of these in each suit. So that's 12 out of 52. But now I got to subtract off for the red cards that are less than 4. Well, there are 3 red cards in hearts, and there are 3 red cards in diamonds. So that's a total of 6 red cards that are also less than 4. So I'm going to subtract off 6 out of 52. So let's see. What does that give me? 32 out of 52? Yes. What's the probability of a king or a heart? So this is the probability of a king plus the probability of a heart minus the probability of the king and the heart, or in this case, the king of hearts. So probability of a king is 4 out of 52. The probability of a heart is 13 out of 52, minus the probability of king and heart, or in other words, the king of hearts, which is really just 1 out of 52. So this would be, what is this, 16 out of 52? That's it. All right, so we got what's the probability of getting a heart? Well, how many hearts are there? There are 13 out of 52. And then I said followed by a, and then the heart followed by a king. That's a really hard problem to do. Because it's supposed to be black king. A heart followed by a black king. So it's 13 out of 52 to get the heart. There's 13 out of 52 to get the heart. And then to get that black king, there's 4 out of 51. So that's a total of what? 52 out of, what is, I forgot what 52. Every good math teacher should know 56 times, or 52 times 51, but I haven't done it in a while. Something like 2652 or something like that. 2652, yeah. What's the follow? All right, this is a dumb question. I thought I changed these questions. I don't know which one you have. This was supposed to be red followed by a face card. This is really not even possible. This was supposed to be a pair. What's the probability of getting a pair? So I feel like I have an old version of this test. So I'm hope if I find any more things, I'm going to have to fix them. But this was supposed to be a pair. So what's the probability of getting a pair? All right, well, the probability of getting a pair. Well, does it really matter what you get on the first one? By a pair, I mean 2 aces, 2 threes, 2 of something. You pull 2 cards, what's the probability of getting an ace? Well, what does that entail? That entails you pulling 1 card and then pulling another card. Now, does it matter what you get on the first card? No, it makes no difference what you get on the first card. You're going to pull a first card, and then I'm going to multiply by it. Now, let's say I pull a 7. So I pulled a 7. How many 7s are left in the deck? 3. Right. How many cards are left in the deck? 51. So what is the probability on that second card I go in, I pull another 7? Well, 3 out of 51. Which is a total of 3 out of 51. So that's actually the answer. That's kind of a tricky question. All right, so Mr. Rolast of Dies a test for any girl wishing to date him. Okay, so I know this is absolutely wrong because there's the rest of the test. So let me see. All right, I'm going to finish this question, then I got to get my real test because this is an old test. So Mr. Rolast desires a test for any girl wishing to date him. They must tell him the probability of rolling the following pair of dice and getting an even odd sum. An even odd sum. Oh, yeah, I forgot about this. An odd sum. This was just supposed to say odd. I should have fixed it. Okay, I'll fix that in class. So what's the probability of getting an odd sum? And I gave you a little hint. In order to get an odd sum, you must have 1 even and 1 odd. All right, so here's how this can happen. Let's look at the die. The die has these possibilities in the sample space. 1, 2, 3, 4, 5, and 6. And then the other red die has 1, 2, 3, 4, 5, 6, 7, and 8. All right. So what is the probability that I get an odd sum? So remember what I just said. That has to be 1 odd followed by an even. Or it could be an even followed by an odd. So, I shouldn't have put a plus. So it could be odd and even, or even and odd. So that's what we're going to do. What is the probability of getting, so this is going to be the probability of even and odd, or the probability of odd and even. Well, even and odd, what's this? Let's see. Probability of even. 1, 2, 3. 1/2. Probability of odd down here. 1, 2, 3, 4 out of 8. Or 1/2. So the probability of even odd is 1/2 times 1/2 or 1/4. Or means plus. And then odd even, well, if the probability of even for this one was 1/2, the probability of odd for this is 1/2. So 1/2 times the probability of even for this would also be 1/2. So that would be 1/2 times 1/2 or 1/4. And if I add those up, I get 1/2. So doesn't that make sense that half my sums would be odd? All right, I'll be right back with the correct practice test. Okay, I got the right version. It did say heart followed by black king. It did say pair. There's Mr. Roloff. All right, let's get through some of this stuff now. Let's go. If the fact that events A and B are disjoint. All right, remember, the one thing you want to remember about disjoint, it is the idea that you have 2 circles, A and B, that never intersect. In other words, the probability that they're disjoint is 0. Okay. Remember what this notation is. This is the probability of not A. Now, what it really means is A complement. the complement of A. In other words, if the probability it's going to rain is 0.81, what's the probability it's not going to rain? Simply 0.19. That's it. If A and B are independent, right? This is one of your tests for independence. Then the probability of A equals the probability of A given that B has occurred. That's your test for independence. If A and B are independent, then the probability of A and B is equal to the probability of A times the probability of B. This is all stuff that's got to be locked into your brain. All right, see what we got here. Now, in this question 13, I did not address independence or not independence. I just said, what's the probability of A and B? Well, the probability of A and B is equal to, now if we use this idea, it's going to be equal to the probability of A times the probability of B given A. That's another one of this is our dependent formula, right? If we don't have independent, then we're going to use our dependent formula. Remember, our dependent formula is really just our independent formula minus that stuff. Okay, so if I got that, all I got to do is multiply probability of A times the probability of B given A. Well, in this case, it's 0.22 times 0.4. And I think that's equal to 0.088. Is that right? I think it's 0.088. Probability of B given A. Wait a second now. Hold on a second. So I know that the probability of A and B is equal to the probability of A times the probability of B given A. Okay. Which means 0.32 is equal to 0.6 times the probability of A. Divide by 0.6 and divide by 0.6. And this I can't do. And I don't expect you to leave it like that. I expect you to give me a nice number. So 0.32, so 32 hundredths, divided by 6 tenths. 0.53 repeating. So we'll just go with 0.53. I could do 5 repeating if I wanted. All right. So now here's what I'm saying. I am asking, are they independent? I have 2 tests. I have 3 tests for independence. So these first 2 are asking independent. I could prove that probability of A is equal to the probability of A given B. If that's true, independent. I can go probability of B is equal to the probability of B given A. If that's true, independent. Or I can go probability of A and B is equal to the probability of A times the probability of B. If that's true, independent. So I got to see what I got here. I got A, I got B, and I got and. I don't see any givens. No givens, no givens. So I'm just going to use this test. The test that's the probability of A and B is equal to the probability of A times the probability of B. Somebody should count the number of times I say the word probability in this video. You'd be like, dude, you just said it for the 1,000th time. I'm going to probably say it 1,000 times. So, does it equal? Now, you might want to say, hey, this is a test. We're going to ask this question. Are they equal? If they're equal, it's independent. If they're not equal, not independent. So, is 0.42 equal to 0.84 times 0.20? Well, let's go over to our calculator. 0.84 times 0.20. 0.168. So does 0.42 equal 0.168? No. Not independent. And I wrote yes for some silly reason. Why did I write yes? Did I do something wrong? Why did I write yes? No, nope, they are not independent. So that's a mistake on my other answer key. Hopefully you found it. Let me know about it. Let's try this one. We're going to do the same test. Oh, wait, hold on. There's probably, oh, I should put a comma here. There's the probability of B, there's the probability of A, and there's the probability of A and B. So we're going to take 0.48. We're going to multiply by 0.12. And does that equal 0.14? So we'll come over our calculator. 0.48 times 0.12. 0.056576. So 0.0576. Does that equal 0.14? Nope, not independent. Not independent. By the way, I meant for this one up here to be point. I know I meant to change this, and I was going to change this to 0.5. If this was, in fact, a 0.5, then you would have 0.42 equals 0.42, I believe. 0.84 times 0.5. Yeah, 0.42. And that's what I meant that to be, but I forgot to change it. So sorry about that. All right. Again, we are given independent events. If I'm given independent events, then that holds that that's true, and that is true. So I can use any one of those ideas. And you should have those things off to the side, making sure you know that you can use any one of those. All right, let's get started on this one. Okay, what do we got here? We have an OR statement, an You should know that as soon as you see an OR statement, you got to write that OR formula. The probability of A or B is equal to the probability of A times the probability of B minus the probability of A and B. Okay, that's not bad. Let's see what we got. Probability of A, 0.6. Probability of B, oops, forgot the plus sign, 0.5. Minus the, well, we weren't given that, were we? But there is a piece of information that we were given. And just like I said before, because we were given this piece of information, I know all three of these things in yellow to be true, which means I can substitute this in for A and B. So I'm going to just replace this. This I'm going to get rid of because they're independent. I'm going to replace it with the probability of A times the probability of B. So let's see, that is 0.6 times 0.5. So let's see what we got. Add these up, I get 1.1 minus 0.3, and that's equal to 0.8. 0.8. All right, moving on. Let's see what we got. I got another OR. Okay, so this one's a little bit trickier. Let's see. Oh, yeah. Star this puppy, kids. This one's going to be on your test. This one's a little bit harder. Actually, this one's quite a bit harder. Probability of A or B is equal to the probability of A plus the probability of B. And just like on the last one, because they're independent, instead of using probability of A and B, I'm going to say minus the probability of A times the probability of B. And the reason I'm going to do that is because I need some room, because there's going to be plenty of room. So instead of having to go, oh, wait, this is the blue thing is the formula, but I can replace it here, I've just already replaced it. All right, so now it gets a little funky. Probability of A is 0.66 plus the probability of B is 0.40. Whoa. Let's back up the crazy train, kids. What am I doing? I gave you the probability of A or B is 0.66. I apologize. 0.66 goes here. The probability of A is 0.4. Plus, we don't know what the probability of B is, so we're just going to replace it with the probability of B, minus 0.4, which is the probability of A, times the probability of B. All right, well, let's move this over. We'll subtract this. That's pretty easy. So I get 0.26 equals the probability of B minus 0.4 times the probability of B. Well, this is like having 1 probability of B minus 0.4 probabilities of B. Well, 1 minus 0.4 is 0.6. So this becomes 0.26 equals 0.6. 1 probability of B minus 0.4 probability of B equals 0.6 probability of B. All right, well, now all I got to do is divide by 0.6. So I'm going to take 0.26 and divide by 0.6. 0.26 divided by 0.6, and I get 0.043 repeating. So the probability of B is equal to 0.043 repeating. I think on the answer key I wrote 0.43. Did I mess up? 0.26. Oh, that's why. It is, notice I forgot. So it's 0.26 divided by 0.6. Not 6. It's 0.43 repeating. So get rid of that 0. Let's just get rid of that 0. So it's 0.43 repeating. Sorry about that. All right. I'm running dangerously low on coffee, kids. This time I'm asking you, are A and B independent? So before, when I said they were independent, all these yellow things were true. Now I'm telling you, or I'm asking you, are they independent? So you need to use one of them to either prove yes they are or no they aren't. If you have things that have givens in them, you'll use these two. If you have an and in it, you'll use this one. Let's see what we got in this problem. It looks like we have an and. So I'm going to use, does the probability of A and B equal the probability of A times the probability of B? And I'm going to even put a question mark here. Does it? I don't know. So let's see. Does 0.3 equal 0.75 times 0.4? Does the probability of A and B? I don't know. Let's see. 0.75 times 0.3. Oh, it wasn't 0.3, it was 0.4, wasn't it? 0.4. 0.75 times 0.4. Got to put the right numbers in, children. Oh, 0.3. So I end up getting 0.3 equals 0.3. So yes, they are independent. All right. Ooh, what just happened? Oops. Went back to the old one. Given that, and that, and that, and that. Okay. Nowhere in here now did I say independent at all. So if I don't tell you they're independent, then you have to assume that they are probably dependent. So in other words, you have to use one of these two formulas. The probability of A and B equals the probability of A times the probability of B given A. Or this one, the probability of B times the probability of A given B. Remember, the dependent formula, if I get rid of this, notice they're really just the independent formula. So if I get rid of this little piece behind here in black, I have the independent formula, probability of A times probability of B. That's not what we have here. So I got to decide which one to use. I'm going to highlight all the stuff I got. So I have probability of A. I have probability of A given B. And I have the probability of B given A. So which one do you think I should use? Clearly, this is the winner. I got to use this one. So I know that this is going to equal the probability of A, which is 0.33, times the probability of B given A, which is 0.1. So I come over to my calculator, 0.33 times 0.1, and I get 0.033. So 0.033. Given A and B such that that and that and that, determine whether A and B are independent or dependent. Okay, but I see an or. As soon as I see an or, I'm going to show that probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So there's two ways to go about doing this. I'm going to do it this way. I know that this is 0.84. I know that this is 0.8. I know that this is 0.2. I just don't know what this is, the probability of A and B. So I'm just going to solve for it. This is 1, so I'm going to subtract off 1. If I put these together, I get 1. So I'm going to subtract off 1, and I get 0.16 equals the probability of A. Excuse me, let me do this the right way, because I don't want to skip too many steps. So let's do it the right way, because I know you're going to get confused by what I just did, and I apologize. So 0.84 equals 1, when I put those together, minus the probability of A and B. So then I'm going to come over here and I'm going to subtract 1, and I'm going to subtract 1. So what I get is, and I'm going to put this over here, 0.16 equals, negative 0.16 equals negative probability of A and B. So really 0.16 equals the probability of A and B. Now, am I any closer to saying that they're independent or not? Well, I am. I have to run one of my tests, though. Remember, one of my tests are right here in yellow, and I'm going to use this test right here. So I want to show that yes, they are, or no, they're not, by showing that the probability of A and B is equal to the probability of A times the probability of B. So does 0.16 equal 0.8 times 0.2? Come over to your calculator, 0.8 times 0.2, and you're going to see that, yes, in fact, they are, in fact, equal. So 0.16 equals 0.16. So, yes, they are, in fact, independent. Another way you could have done it is this way, which probably would have been a little bit faster. And this is one of my students showed me this one, and I missed this, and I think it's actually a pretty cool way. So, Miss Matthews, nice job finding this one. That was kind of a cool problem. What she said was, and I thought this was really smart of her, so give her some props when you see her, because this makes this problem a little bit easier. She said, well, if they are independent, doesn't this really just be probability of A times the probability of B? And I said, yeah. So then can I just show that 0.84 equals 0.8 plus 0.2 minus 0.8 times 0.2. If that's true, then they're independent, because I just substitute this in, assuming they were independent. So then I end up with 0.84 equals 0.84, and because those are equal, then I know that this must be true. That's another way to do it. Determine whether, I'm going to do it the other way, though. I like that way. It's a little bit longer, but it gets me more practice. So the more practice, the better. A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So what is this? 0.65 equals 0.4 plus 0.3 minus, we don't know what this is. Now I am going to skip a few steps this time. This is 0.7. So I'm going to subtract off 0.7. So I get 0.05 is equal to negative probability of A and B. Or in other words, the probability of A and B is equal to 0.05. Well, what I need to show is, does that equal these two multiplied together? So if I take 0.4 and I multiply it by 0.3, does that equal 0.05? And the answer is clearly no. So they are not independent. All right, here we go. We got a two-way table. There's a two-way frequency table. What did I leave out? I left out the totals. That's annoying. Wait a second. Okay. I got lots. So problems 23 through 26 all use this. Actually, 27 use all this. So this should say through 27. But I'm going to need those totals. So let's see. 57 and 30 is 87 and 5 is 92. 46, that's 68. And so what is that? 75? Am I getting that right? 29 and 75. And then I've got 43 and 35 is 78, so this is 88. If I add these up, I get 180 plus 75 is 255. So I did that good. And so down here, 12, and so that's what? 43.55. If I add these up, I get 7, 6, 87. And here I get 3, 2, 6, 11. So let's see, 113 and 87 is 200 and 255. So I didn't give you the totals, so you actually had to come up with those totals. So let's get through these. What is the probability that that a person is between the age of 25 and 50? 25 and 50, there's 88 of those. So 88 out of 255. Oh, wait. Sorry, kids. Sorry. I just did this part. Between 25 and 50. That's 88. But I didn't see that it's and. So 25 and 50 are these. And over 100 are these. Well, which is the one that gets doubled? The one that gets doubled is the 10. So this is 10 out of 255. All right, let's try this one. Snaps over 100 times. And they are between the ages of 16 and 25. Oh, that's 46 out of 255. All right, now wait a second. Now, as soon as I see this given, now I want to write this a little bit differently. So this is probability that they're between the age of 10 and 15, given they snap between 0 and 25 snaps. So that means between 0 and 25 snaps is my new universe. So 0 and 25 snaps is my new universe. So I am not allowed to look at any of this. Not allowed to look at this. This is only thing I can look at right here. Well, that makes my denominator 55. And then how many of them are between 10 and 15? 5. 5 out of 55. Let me get rid of my blacks now. Okay. Now, is between the age of 25 to 50 or snaps over 100 times. Wait a second. Ors are a pain. So if I do it ors, that means it's the probability of 10 to 15 plus the probability of snaps more than, snaps between 0 and 25 minus the probability there between 10 and 15 and snaps 0 to 25. So I got to find out these three probabilities. Well, let's see. What is the probability that they're between 10 and 15? 10 and 15, 92. So 92 out of 255. Plus snaps 0 to 25 times. 0 to 25 times is this 55 down here. So I got to add 55 over 255. Minus between 0 and 15 and so between 0 and 25 and between 10 and 15. So that's the 5 out of 255. So 92 plus 50 is what, 142? So this is 142 out of 150. No, 255. All right. Woo. All right, so this one I made you count. So I'll do this real quick. This is 12. This is, I don't know what this is. This is 44. And let's see. 0, that's 4, and that's 3, so that's 10. 8, 2, 3, 4, 10, 18. This is 18. Let's see if that makes sense. 18 and 38 is 56, and 44 is 100. Okay, good. What's the probability they fly? Oh, 38 out of 100. What's the probability they're female? 52 out of 100. What's the probability they're male and invisible? So here's male. Here's invisible. What's the one? There it is right there. 12. So 12 out of 100. Oops, lost my 0. So what's the probability they're female and other? So female and other. Where's the crosshatch? 8. 8 out of 100. Now, fly or female. Now, be careful. This one's hard. So it's the probability of fly plus the probability of female minus the probability fly female. Ooh, a fly female. Fly and female. All right. Probability of fly. Ooh, let me get rid of all these extra stuff. Probability of fly is 38 out of 100. Notice I gave you a little extra room here, right? Plus the probability of female, 52 out of 100. Minus the probability of a fly and female. Fly and female is this 12 right here, right? Fly and female. So 12 out of 50, out of 100. So that's 40. So this is 78. 78 out of 100. Other or male. So this is the probability of other plus the probability of male minus the probability of other and male. All right, probability of other, 18 out of 100. Remember, we got to pick this number down here. The probability of male, well, there are 48 males, 48 out of 100. Minus the probability of an other male. Well, here's the other males right here, 10 out of 100. So let's see, that's 8 plus 56. So 56 out of 100. All right, I got 2 left, the givens. Now the givens are a little bit different. Remember, when I use a given, my denominator is not going to be the 100 this time. Anytime you have a given, we're going to restrict what we look at. So I'm going to do that using this big, bold black marker. So my given is that it's fly. The only thing I'm allowed to look at is fly, even though those numbers popped up ahead. The only thing I can look at is fly. Okay. Then my denominator, or everything, has to be 38. What's the probability they're male and fly? 26. Now let's see the next given. The next given is that they are, well, I want to know what it is, other given female. So the only thing I'm allowed to look at is female. Can't look at all this. Well, what's my total for female? My total for female is 52. And what's the other for 8? So 8 out of 52. I just realized I didn't put a relative frequency table in this thing. This one should have been a relative frequency table. So if I had made this one a relative frequency table, these would all be out of 200, so whatever. Let's just go. Probability of brown. Brown. Well, remember, the grand total here is 200. So the probability of brown is 90 out of 200. Uh-oh, I'm already going to the given. So let me start with my givens. I'm given female. The only thing I can look at is female. So if I can only look at female, my denominator is going to be 90. My numerator is, I want green female, 10 out of 90. Yes, I can reduce that to 1/9, but why bother? All right, so my next given is blue. So I can only look at blue. Can't look at brown, Can't look at any of this. I can only look at blue because blue was my given. So blue is my new universe. It's the only thing I'm allowed to look at. And that's 80. And then what's male and blue would be 40 out of 80. And you could reduce that to a half if you want, but there's no reason for it. We'll just leave it the way it is. All right, now we're doing ands. So ands are where they're going to overlap. Male, brown. Where do they overlap? Oh, 50. 50 out of 200. Remember, the only times the denominators are going to change is when we got a new universe, a new given. Otherwise, my universe is still out of 200. Green and female. Female, green. There's the one right there. 10 out of 200. Now, the ORs are always trickier. You have to come up with a formula for OR. So probability of female plus probability of green minus the probability of female and green. All right, probability of female. Female, 90 out of 200. Plus the probability of green, 30 out of 200. Minus the probability of female and green. Well, female and green is just this 10 right here. So 10 out of 200. So that's 110 out of 200. And finally, male or brown. So we're going to do probability of male plus the probability of brown minus the probability of male and brown. Let's see, the probability of male, 50 out of 200. Plus the probability of brown, 90 out of 200. And out of brown males, 50 out of 200. So what is that? No, wait, so what did I screw up? The probability of male, wait. Oh, that's what I screwed up. The probability of male is 110. I knew I screwed something up. 110. The probability of brown is 90. Now, if I added those up, I'd have 200 out of 200. But I got to subtract off this 50, so that's 150 out of 200. Oh, and then so here, this question. So what are we going through, 40? I said through 40, and I'm going all the way down to 44. So, okay, whatever. I decided to add a few more questions. Is the fact that a person has brown eyes independent of them being male? What we're trying to figure out is the probability of brown equal to the probability of brown given male? Well, the probability of brown is 90 out of 200. Now I got to figure out what is the probability of brown given male. So because of that, my new universe is male. I'm only allowed to look at male because male will be my new universe. So what is the probability of brown given male? Brown given male. Well, my total is 110. So does this equal 50 out of 110? Well, as it stands, it's really kind of hard to tell. So I'm going to go to my calculator. I'm going to go to my calculator. And I'm going to do, what is it? 90 divided by 200. So I get 0.45. That was an easy one. I should have just 0.45. Does that equal 50 divided by 110? 0.45454545. So, oh yeah, I did that one on purpose. Are they equal? They are not, because remember, this is 45, 45, 45. That's just 45. So no, they are not independent. Not independent. All right, let's try, is being a female independent of having green eyes? So is the probability of female equal to the probability of female given green eyes? Because if they're independent, that has to be true. I could do the probability of green equals the probability of green given female. Or I could do the probability of green and female is equal to the probability of green times the probability of female. I could run any one of those three independent tests. So let's see what we got. The probability of female. Probability of female is 90 out of 200. Does that equal the probability of female given green eyes? So I got to get rid of everything but green eyes. Can't look at this. Can't look at this. So now my denominator is 30. And my numerator is female and 30. So that's 10 out of 30. So I know that right is just 0.3 repeating. 90 out of 210 we already showed was 0.45. Do those equal? So no, this is also not independent. All right, I think we're down to the last 3 questions. But let me take a pause, my last pause. All right, kids. Mutually exclusive is the same as disjoint. Disjoint. Well, let's see where that comes into play. Uh-oh. I got probability of an OR right here. I have the probability of an OR. So because of that, that means that the probability of H or M, I'm going to write this formula down, is equal to the probability of H plus the probability of M minus the probability of H and M. I know that looks like ham. There it is. H and M. All right. So how the heck am I going to do this? Let's see. The probability of H, 0.5. The probability of M, no idea. The probability of H or M is 0.6. So what is this? Well, if they are disjoint, the only thing you have to remember about disjoint is the probability of H and M is equal to 0. So if they're a disjoint, this is really just 0, or I don't even need it. So I subtract 0.5 and I get the probability of M is equal to 0.1 because I can just subtract 0.5. All right, so what happens if they're independent then? Okay, independent, this is a little bit trickier. I probably should have given you more room on this one. Independent, that means the probability, I'm going to use that same formula, the probability of H or M is equal to the probability of H plus the probability of M. But this time, because they're independent, the probability of H and M is equal to the probability of H times the probability of M. So I'm just going to replace this with the probability of H times the probability of M. And now I got some serious work to do, and I did not give you enough room on this one. So let me start over here. I'm going to try to make some room. The probability of H or M is 0.6. That's this piece. Is equal to the probability of H, which is 0.5, plus the probability of M, minus the probability of H, which is 0.5, times the probability of M. Well, I'm going to subtract this 0.5. I'm going to bring it over. So I get 0.1 equals 1 probability of M minus 0.5 probability of M. Well, we did this one before. We did something very similar to this. This is 1 probability of M minus 0.5 probability of M. So that gives me a 0.5 M. That's 1 probability of M minus a half a probability of M. That gives me a half a probability of M. So I get 0.1 is equal to 0.5 times the probability of M. Remember, this is like 1x minus a half x. It's just equal to a half x. Well, I divide both sides by 0.5, and I end up getting 0.2 is equal to the probability of M. And I definitely didn't give you enough room. So, mutually exclusive. Probability of S and M equals 0. In this case, the probability of S and M is equal to the probability of S times the probability of M. So we're going to use these same formulas. We're going to use the same ideas. I'm going to try to sneak up. So this is the probability of sum, S-U-M. S or M is equal to the probability of S plus the probability of M minus 0. Because it's really the probability of S and M, but it's 0. So I don't need to worry about it this time. These are the easy cases. This is 0.7 is equal to 0.3 plus the probability of M. So the probability of M is equal to 0.4. And finally, independent. Okay, see what we got here. We're going to use the same formula, but in this case, we're going to use the probability of sum, S and M, S or M is equal to the probability of S plus the probability of M minus, now it's really the probability of S and M, but remember, because they're independent, I'm going to use this. Probability of S times the probability of M. And these are the harder ones. So 0.7 is equal to 0.3 plus probability of M minus 0.3 times the probability of M. So I'll subtract this 0.3 over. I get 0.4 is equal to probability of M minus 0.3 times the probability of M. So once again, I have one probability of M minus 0.3 probability of M. So what I really have here is 0.7 equals 0.4 equals, now let's see, what is 1 probability of M minus 0.3 probability of M? So that's 0.7 times the probability of M. Divide by 0.7. And I wrote down on your answer key 4/7 equals the probability of M. You could have, geez, you know, 0.5714 is just such an obnoxious number. I decided to leave it as that. Oh my goodness, the last two problems. Okay, because I said they're independent. Because I said they're independent. That means I'm allowed to use that the probability of A and B is equal to the probability of A times the probability of B. And that's probably what I'm going to use in this case, because I got an OR again. Oh, these are the same problems I just did. So you should be able to do these now. If you didn't do the last two, then you better be doing these two. And by the way, I just realized I'm being really boring in this video, and I apologize. It's late at night, and I'm very tired for some reason. I went swimming last night, and I'm just so tired today. So I'm apologizing. I don't have enough coffee. I'm out of coffee. It's terrible. So probability of A or B. Practice it one more time. Equal to the probability of A plus the probability of B minus the probability of A and B. But again, we're going to replace this. I'm just going to replace this with the probability of A times the probability of B. So, what's the probability of A? Well, probability of A or B is 0.68. That didn't work. 0.68. Probability of A is 0.4 plus the probability of B minus 0.4 times the probability of B. Now, I'm going to try to speed things up a little bit. I'm going to subtract 0.4 here. So I get 0.28 equals. Now, again, this is 1 probability of B minus 0.4 probability of B. That's 0.6 times the probability of B. Divide by both sides by 0.6. And I get the probability of B equals 0.28 divided by 0.6. 0.46 repeating. All right, this last one, please, if you haven't done any of the last couples on your own, do this one on your own and see if you can get the right answer. So, this is going to be the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And again, I did like 4 of these same problems in a row, so by now you should be a genius at them. This is 0.76 Does that equal, I don't have A this time, so I did things a little bit trickier. The probability of A plus 0.52 minus, now remember, we're going to replace this with the probability of A times the probability of B. So this is probability of A times 0.52. All right, so I'm going to subtract this over. And I get 24 equals 0.24 equals probability of A minus 0.52 times the probability of A. All right, I just like putting the number in front. So this is 1 probability of A minus 0.52 probabilities of A. That equals 0.4. So I get 0.24 equals 0.48. Again, 1 minus 0.52 equals 0.48 times the probability of A. Divide by 0.48. Divide by 0.48. And 24 divided by 48 is, in fact, a half. So the probability of A, oops, that's where my head is. The probability of A equals 0.5. All right, kids, I hope you did okay. I hope you know what you're doing, and I hope you're ready for the test. Study, study, study. Get those formulas down, okay? I'm just going to write them down one more time for you. Let's see if I can get some more room here. What do you got to remember? If I tell you disjoint, which is the same as mutually exclusive, you need to remember that the probability of A and B is equal to 0. If I tell you independent, you're going to be using one of these three. The probability of A is equal to the probability of A given B. Or the probability of B is equal to the probability of B given A. Or the probability of A and B is equal to the probability of A times the probability of B. Some way, somehow, you're going to use those. If I give you an OR statement, probability of A or B, you need to write down that formula. Equals the probability of A plus the probability of B minus the probability of A and B. And finally, if I don't give you, so this is if I give you this, or anywhere in there it says or. And if I don't give you anything else, then they're probably dependent, and you have to use this one, the probability. Oh, I'm not going to have enough room if I use that stupid marker. I'll use the small black one. The probability of A and B is equal to the probability of A times the probability of B given A. And I'm going to remind you how to do this. Or this one, probability of A and B is equal to the probability of B times the probability of A given B. Now, how do you remember that? This is how you remember it. If I get rid of these, this little part, this part of here at the end, and I just look at this, isn't this the independent formula? That's the independent formula. However, when I add this piece in, this little piece at the end, this now makes it the dependent variable. Now, I'm not going to tell you dependent. I'm just not going to tell you it's independent. Okay? You're going to have to be able to put them together. All right, kids, that's the end of the video. I hope you remember it. Hit the subscribe button. Hit the like button. Leave me a comment other than, what? All right, kids. It's been fun spending time with you. Not really. I'm just kidding. Go away. No, really, go away. All right, I'll go. Bye.